Okay, we'll be doing this problem again. Some part of problem we have done, but we'll continue to do it from the beginning itself. So in this power term, specifications for the different equipment, so the devices or components have been given in the system. Components have been given in the data, and what he's telling us to he's telling us to draw a per unit reactance diagram of this one. So we have to choose a base. Let the base MVA be. Last time we have taken the same base MVA. Let the base MVA, that is S base, is equivalent to 30 MVA, and base KV, that is V base, is equal to 33 kV. Where from this is? This is from the transmission line. So we have selected the base values 30 MVA and 30 MVA and 33 kV voltage from the what you call 30 MVA is a complex power base or apparent power base. It will remain same throughout the power system. Everywhere it is same, but voltage base will change according to the transformation ratio when we will encounter various transformers. So it's in the transmission line. 33 kV is in the transmission line. Okay. So let us first find the base KVs, as we will be always doing. So base KV in generator 1. This is here a generator 1, base KV in generator 1 circuit. So that will be, we'll move from where? We'll move from the transmission line, 33. So this side of the transmission, T1 has to be, what is the ratio of T1? 33. So this side it is T1. This side of T1 is 33. This is 11. So it will be 11 by 33. So that will be 11 kV. So on the generator 1, the base kV is 11 kV. Similarly, we'll find the base kV in circuit of generator 2. Generator 2, 3, it will be same, and that load also circuit. So we are moving from here. So this has to be 33 kV. This has to be again 2 is here 6.2. So that will be base kV is here 33 multiplied by 6.2 by 33. So that will be 6.2 kV. So base kV will be 6.2 on the generator 2 side. So let's find now all the per unit values of reactance or impedance. So what we will be doing, we will now convert all parameter, sorry, this is not parameter values to per unit on the common system base specified above. Above means we have specified 2 bases. Those bases will be there. So one by one we will start. So first will be, okay, is it correct? Okay. Find same circuit. Okay. Now first we will base reactance of the transmission line. of the transmission line. So transmission line, the actual value is given in ohms here. So we need to find this. You can see transmission line 20.5 ohms per phase, and base value is 33. So that we write V base square, that's a per phase base, divided by S base. So V base here is how much? 33 square divided by S base is 30. We have already chosen a 30 base. So per unit reactance will be, therefore, per unit reactance of the transmission line that is actual value is in ohms, you can see, sorry, actual value is in ohms, you can see ohms per phase 20.5. So you can write that 20.5 divided by this base value, that will be 33 square, and this will go up 30. So this will come out to be J, can write down this is J 0.565 per unit. 0.565 in per unit. So next is per unit reactance of transformer T1. Again, clearly you can see what is the per unit, how we have to find the per unit value. See, transformer T2, again it's in actual values, 33 by 15.5. Now per unit values is not given here. See, there is only difference between previous and this question is that the per unit values is given in actual values, so we have to use the base values like we use for the transmission line. Same thing we have to do. So if it is given in per unit, then you can find that formula Z per unit new into SB new divided by SB old divided by V base old divided by V base new whole square. But here it's an actual value. That's why I am using this type. So per unit value of transmission for the transformer 1 will be V base square divided by S base. What is the base in this transformer 1? Transformer 1 is this one. You can choose either the primary side. This is an 11 kV to 33 kV. Transformer 11 kV to 33 kV. So if you choose 11 kV, then base value is 11. If 33, then base value is also the same thing. So per unit value will be V base. Sorry, what's the transformer? Yeah, 11 kV. Okay. Yeah, same thing. V base, if you go for the 11 kV side, V base square, I'm not writing the formula again, V base square divided by S base is same. So therefore actual value, this is the base value per unit, this is the base value I'm writing here. So if I write the per unit reactance value, that will be actual value. What is the actual value in the transformer? T1, that is 15.2 per phase on the HT side. 15.2. HT side is this one. So we are using the same. We have to use the base of the HT side on high tension side. So high tension side is 33 kV. So base value has to be chosen 33 kV here. It is specified. That's why I am just marked this. So actual value is, sorry, what is the value of the 15.2? So that is J 15.2 divided by this base value 33 square multiplied by 30, and this comes out to be J 0.419. Yeah, calculate already 0.419 per unit. So very important, you have to find base values every time now, because the per unit old values are given in the actual values. So same formula as the transmission line will be used. So next is per unit reactance of transformer. I will write now directly. Per unit reactance of transformer T2. So that will be, what is the value here? You can say actual value of the T2. Actual value is 16. This is also on the HT side. ht of T2 is left side, so it is 33. So 33 square divided by 30, that is base value. So actual value is 16, J16 multiplied by 30 by 33 square. So I'm writing like this directly now. So that will be actual value divided by base value. So that will be J 0.44 per unit. Okay. Next is per unit reactance for the generator G1. Generator G1. Again, what is the actual value? J generator G1, you can see generator G1 actual value is 1.6 and base value in the generator is 11. So actual value 16 divided by 11 square by 30, that will be 16 into 30 divided by 11 square. So that is J, not 16, it's 1.6, sorry, 1.6 into 30 by 11 square. Why? Because generator base value is 11. So that comes out to be J 0.397 per unit. Next is per unit reactance of generator G2. So what is the actual value in the generator G2? See, generator G2 is here. Base value is what? 6.2. So V base square, that will be 6.2 square divided by S base, 30. S base is same. So what is the G2 actual value? Actual value in old per unit is 1.2. 1.2 multiplied by, that is 30 divided by 6.2 square. So we can write directly now. 1.2 J 1.2 multiplied by 30 divided by 6.2 square. So this comes out to be J 0.937 per unit. Next is per unit reactance of generator G3. So how we can write again? What is the actual value of G3? You can see here 0.56. So J 0.6 divided by base value is same. So you multiply it by 6.2 divided by 30 square. Sorry, 30 divided by 6.2 square. J 0.56 30 divided by, again base value is same, 6.2 square. That comes out to be J 0.437 in per unit. So these are the generators. So new will be the loads. So you should remember how to calculate for the loads. I'll just add a page. Okay, load is new for you, so just should know how to calculate for load A. Okay, and have a look here. Load A is here. This is load A and this is load B. What is the base value? 11. And load A, what is the voltage value? 11 kV. So we can write it. Voltage is in per unit. How we can write? Actual value, that is 11 kV. Base value is also 11 kV. So that is 1 per unit. Very clearly. Voltages, we have to find the base value. Actual value divided by base value. Actual value as load A is 11. Base value is on the generator one side is also 11. So it is 1 per unit. Power factor is given. Power factor cos phi, that is cos phi is given 0.9 lag. It is given in the numerical itself. So you can find sin phi from here. Sin phi will be under root of 1 minus cos square phi, and this comes out to be under root of 1 minus 0.9 square. And if you want to find the sin phi, the calculated value is 0.436. So real power is real power in per unit, how we can write? So that can be written P equal to actual value of the real power. Can see in load A, actual value is 40 megavolts. So actual value is 40 megavolts, 10 to the power of 6. Base value, load A, base value is power, complex power base will be the same because real power, reactive power, the base value is always complex power. So that will be 30 into 10 to the power of 6, 30 megavolt ampere. So this and this and cancelled. So 4 by 3 will come out to be 1.333 per unit. Okay. So I will just, for your information, I have told you already number of times, the P, that is the real power in per unit, can be found by actual value of the real power. What is the base value? Base value is also always in a complex power base, S base. So base in real, reactive and complex will be S base. Same bases will be used. That I have already explained earlier. Okay. So reactive power we can find from here. Reactive power. Reactive power is given by Q, and Q we know already, we know that is P into tan of phi. Okay, that expression we have already derived. How? You can hear, for your information again, those VIP is equal to VI, sorry, cos phi, Q is equivalent to VI sin phi. Okay, so what we have to find? P by Q. P by Q is, or yeah, P is equal to VI, P by Q is cos by sine. Okay, so P is equal to VI Q. Sorry, a bit mistake is there. It's just okay. No need to. So P by Q is VP. Real power is VI cos phi. Q is VI sin phi. So Q by P is tan phi. One and the same thing you can do by any. Q is equal to P tan phi. So just for your information, how we have got it. So Q is equal to P tan phi. You divide it equations and then you can get this. So Q tan phi is, P is, we already know in per unit is how much? 1.333 in per unit. Tan phi is very simple. Cos by tan phi is sin by cos. Sin is 0.436. Cos is how much? 0.9. So if you calculate it, the per unit value of reactive power will be 0.6456 in per unit. This is the reactive power. So next is per unit resistance. Per unit resistance is RPU. RPU will be VPU V square by PPU. How? Because general expression is R for what? R is equivalent to V square by P. Power has 3. P is equivalent to VI. P is equivalent to I square R. P is equivalent to V square by R. So from there only you will get RPU is equivalent to, because I have told you whatever the relationship exists in the absolute value, same will exist in the per unit values also. So RPU will be VPU square divided by PPU square. So this is 1 square. VPU is 1. We have got VPU 1. You can see here. This is your VPU. You can write in per unit 1. PPU in per unit is 1.33. So you can write here 1.333. So that comes out to be 0.75 per unit. So this is clearly 0.75 per unit. Similarly, per unit reactance you can find. That is XPU. XPU can be similarly written as VPU square divided by QPU. because that's related to the reactive power. So we can find VPU square by QPU square. That's the same relationship we use in absolute systems. So 1 square divided by, that will be QPU is 0.6456. This is 0.6456, and this comes out to be 1.549 per unit. So you have got RPU also and XPU also. So similar approach should be for the load B. For load B, this is the way you have to analyze the loads A and B. So voltage here in base value of the voltage in the per unit. So per unit value will be actual value. You can go to the load B here. Load B, where is load B? Okay, load B is here. Actual value is 6.6. What is the base value on this side? 6.2. So 6.6 divided by 6.2. Actual value here, voltage is 6.6 and base value is 6.2. And this will come out to be 1.065 per unit. So VPU you have got. Next, real power. Same thing what we have done previous load, we have to do same thing. Real power P will be actual wall of the power, actual value of the, what is the, just 40 again. Actual value is 40 megawatts and base value is 30. That will remain the same, 40 by 30, and that comes out to be 1.3 per unit. Next, we have power factor again. Cos phi in this case is, let's see how much power factor is given in this case, 0.5 power factor lag. So we can use 0.5 lagging power factor and we can derive the sin phi. Sin phi will be given as under root of 1 minus 0.5 square. That will come out to be 0.806. Next real power we have got in per unit. Cos phi and sin phi also got. We can get the reactive power. Reactive power Q is equal to P tan phi. P is how much? 1.33 again. 1.3, sorry. 333, actually it is same. Multiplied by here also 333. Multiplied by tan point, sin is 0.806, cos is 0.5, and reactive power comes out to be 2.31 per unit. So similarly, per unit resistance we can find. Per unit resistance is RPU. RPU is nothing but VPU square by PPU. That's real power in per unit. And that's 0.05 square divided by PPU is 1.333. And that comes out to be 0.85 per unit. So next is per unit reactance. XPU. Two 2.35, 31. Okay. So now you can draw the per unit reactance diagram. Per unit reactance diagram. We'll draw on the next page. So loads can be drawn in a parallel. That means resistance and reactance can be drawn in the parallel. So we have generator, bus bar. So these will be parallel. Then we have transformer, transmission line, transformer, 2 generators and 1 load. So loads have to be modeled in a parallel fashion. I will show you how to model these loads. So Number one will be generator. Okay. Sorry. Okay. Okay. Number one will be generator. Reactance of generator, and then we have voltage source of the generator. Okay. Next is loads. How we model the loads, I have told you, you can model them in a parallel fashion. That means resistance, and here it can be reactance. Okay. Then we have a transformer number one, transmission line, then transformer number two, transformer number one, transmission line, transformer number two. Then again we have loads. We model them in parallel. Okay. Then we have two generators. So there will be reactance of the generator, and then there will be voltage source of the generator. And then one more generator. There will be reactance of the generator, and then the voltage source of the generator. And then this is the grounding, common grounding. Okay. So reactance of the generator number one we can draw, and then first let me draw the sources, voltage source. Okay. So reactance of the generator number one, how much is this value? So J 0.397, you can check them per unit. So this is EG1, generator 1. Resistance of load A, reactance of load A. So resistance of load A is 0.75 per unit. Reactance is J 1.549. Then we have transformer number one, transmission line. Then we have transformer number two. J 0.419 per unit. Transmission line is J 0.565 per unit. And then we have J 0.44 per unit. Then load B, resistance modeled in parallel. So we have 0.85 resistance. Reactance we have J 0.49. Generator number two, we have reactance. Okay, generator number three, we have reactance again. So here we have generator number two, J 0.937 per unit. This is per unit. And we have EG2, generator number 3, J 0.437, and this is EG3. So this is the per unit reactance diagram. Very clearly, everything should be clear. So this was about this numerical, very simple numerical. Okay, let's move to the another simple problem. There are some more conventional problems that I will give for the homework. So per unit impedance of armature. Next problem is, okay, before this we had another problem or no? Okay, we have this and then we have one more minute for a per unit given. Okay, so fine. Let us do them. पहले तो ये है. Okay, per unit impedance of an armature, okay, corresponding to the base value of 13.2 kV and 30 MVA and 0.2 per unit. The per unit value of impedance for the base value of this. So new base values have been given. Old, you have to, very simple. This is one of the gate questions. So old values are, what are old values? We'll write first. That means S base old is 30 MVA and V base old will write them like this. Clear cut 1.13.2 kV very clearly here. Per unit impedance of armature to the base value. These are its own base values. The per unit impedance for the base value of this. So whatever you have to find, that means those are new values. Whatever the earlier data is, that's for the old values. And XPU old is it is given J.2 per unit. Okay. So what are the new values now? So these are the new base values. New base values are as base new he is telling us 50 MVA. V base new he's telling on 13.8 kV base voltage. We need to find the XPU new. XPU new is equal to, what is the formula? We write the formula first. XPU old multiplied by S base new divided by S base old multiplied by V base old divided by V base new whole square. So XPU old is given here, that is J.2. S base new is 50. S base old is 30. V base old is 13.2. V base new is 13.8 whole square. So this comes out to be, this comes out to be J.305 per unit. So that's the answer you have to write. Very simple numerical. Okay. Next is for a given per unit, for a given base voltage and the base volt ampere. That means base voltage is its own old data, old base voltage and old base complex power base. The per unit impedance value of an element is X. Element is given as X. What will be the per unit impedance of this element? What will be the per unit impedance of this element when the voltage and the voltage ampere both are doubled? That means bases are doubled. So what we can write here, it is given that ZPU is, earlier value is X. Now both of them are doubled now. So XPU new, how we can find? We know formula is XPU old. So that's in front of us. XPU old is X into SB new divided by SB old multiplied by V base old divided by V base new whole square. So XPU old is X. Now if both the base values are doubled, old XPU he is telling, see, base values he is giving. For a given base value and the base voltage ampere, the per unit impedance both is X. That means S base old and V base old, both are X. So, but now this value is doubled. New is doubled. So this will be 2X. Old is X. So old is X. New is 2X whole square. So old values are all X. New values are 2X. Oh, sorry. One mistake is there. What I have done is that when we take voltage values, they have to be taken another variable, because they can't be same. Another variable we have to take. So let this be Y and this be 2Y. That's why one is other, new is the double one of the old, but variables have to be different. So this X and X gets cancelled here, and this will be X into 2. Y and Y gets cancelled. This will be 1 by 4. So that will be X by 2. So earlier it was X, new will be, so XPU new, 4 options will be there. So out of the 4 options, you have to choose the option that the new base, new reactance value or new impedance value will be half of that of the earlier. So this is also one of the gate questions that's normally asked in the gate examination, this type of questions. Okay, so we have one in the gate, I think 1997. I have not written the problem, but it is a very simple problem. Gate 1997, we have problem. Today's fourth problem is this one. Problem number 4th. What's the problem? Problem is the per unit impedance of the synchronous machine. Per unit impedance of the synchronous machine is given as 0.242. Okay, if the voltage base is increased by 1.1 times, the per unit value will be, what will be the per unit value new? So old value we know. What's the old value? XPU is given as 0.242. J you can write, no problem. So what is the formula? We'll keep on repeating the formula so that we can memorize it. XPU new is XPU old multiplied by S base new divided by S base old multiplied by V base old divided by V base new whole square. This is the way to find XPU new. So XPU old, what we have, it's very clearly given as 0.242. This is 0.242. New is, you can see here, if the base value is increased by 1.1 voltage base. So it has not given any information about the S base. So we'll keep that a constant variable X. S base new is X, S base old is also X, because no information is given about it. So we will choose them same value multiplied by V base old. Now he's telling V base old, if it is, let us say the V base old is Y. It is increased, new value is 1.1 times that of the old whole square. So here we can find 0.242 multiplied by, this will be 1 multiplied by 1 by 1.1 square. So when you find this value, this point value comes out to be 0.22 per unit, J 0.22. So XPU new is J 0.22 per unit. This is the GATE 1997. This question was asked. Very simple question. Okay. So we'll continue to do some more numericals. Let's talk about the GATE 1991. This numerical has been asked. The numerical is F5500 MVA, comma 11 kV synchronous generator has 0.2 per unit synchronous reactance. So the per unit synchronous, the per unit synchronous reactance at the base value of 100 MVA and 22 kV is, what is this new value? You have to find it. Very simple numerical. Mansha?
Yes, sir.
Okay, tell me how to solve this problem.
So we are given XPU old 0.2. We will apply
No,
these values to the formula straight
no,
away.
what is the S base? So
S
old S
base
base.
S base old is 500 MVA,
Okay, whatever I am telling, answer those things. What is the V base old?
11 kV,
Very good. So what is the XPU old?
0.2 per unit.
0.2. Very good. Okay. So what is the formula new formula it for it? Shabash, jaldi jaldi.
XPU new is equal to XPU old into SB new divided by SB old into V base old divided by V base new whole square.
Very good. So this will be XPU old into S base new, S base old, V base old, V base new whole square. So XPU old is 0.2. Okay. As base new, that is 100. You have to find on this 100. Old 500. V base old 11. V base new 22 whole square. So that value comes out to be 0.01 per unit. Very simple numericals. Okay. So XPU new is okay. So these are few of the problems. Okay. So एक और just yeah. लेट मी डू द लास्ट न्यूमेरिकल. उसके बाद देखते हैं अगर कोई रह जाता है तो खास नहीं है. फिर उसके बाद दीज आर द इम्पोर्टेंट प्रॉब्लम्स वी हैव डन. गेट 2014 में एक प्रॉब्लम आई है लेटेस्ट. गेट 2014 में है ये प्रॉब्लम. लिख लेता हूं मैं, ज्यादा बड़ी नहीं है. A three-phase star connected load is drawing power at voltage of 0.9 per unit. Voltage value is given per unit. And 0.8 power factor lagging. ठीक है, जो थ्री फेज लोड है उसके ये these are the ratings of the three phase load. The three phase power base and base current are 100 MVA and 437.38 amps respectively. ठीक है. सो ये किसका डेटा है? थ्री फेज पावर बेस एंड दिस. द लाइन टू लाइन वोल्टेज इन केवी विल बी What's the line to line voltage? You have to find it. So let's do this numerical. Very important numerical, this one. What we have given, basically, what is given to us? VPU is given to us. How much? 0.9 per unit. It's very clear from the star connected load. Cos phi has been given. How much? 0.8 lag. Then what else have been given? S base. That is MVA basis 100 megavolt ampere. Okay. And current has been given here. See, a bit different question is there. The three-phase power base is fine. Three-phase power base is 100 MVA. And current base has been given. So I base is, it's a different question a bit. I base has been given as 437.38 amps. Okay. But we know in a three-phase system, S is under root 3 if we are in line V to I, VI. So we can write S base as same. Whatever the value, whatever the expressions are in actual, same will be in the per unit or base values also. V baseline, I baseline, very simple. So out of this, S we know already. So we can find V base because we know that we do not know the base value of the voltage. That's what is aim, our aim to first find. So that will be S base divided by under root 3 I baseline. Sorry. So this is 100 MVA. S is 100 MVA very clearly here. Under root 3 I is 437.38. So we can obtain the base value here, 132 kV. So base value here is 132 kV out. This value comes out to be 132 kV. So V line to line in kV, V per unit multiplied by V base line to line. So actual value is what? Base value into per unit value. That's per unit value is actual value divided by base value. So actual value will be per unit value multiplied by the base value. That's what we have done. Per unit value is 0.9. Base value is 132. And with this V line to line in kV, you can obtain is 118.8 kV. So that's what we had to obtain. This is a very simple numerical. With this, we are going to conclude today. So we'll continue maybe one or two problems. We'll be doing more, and then we'll continue with the next chapter. So this chapter ends here only with a comprehensive. We have done all the numericals in detail. If anybody has a still problem, he can tell. So first, let me stop the recording.